Okay, continuing right along with Mercury. At the end of the last video, I was discussing how they look pretty similar from the surface, but don't judge a book by its cover because there's a lot of differences in these two celestial bodies, a few of which are listed here. Um, Mercury is bigger and more massive than the Moon, so I mean, again, you don't have to memorize these numbers, but write them down for your notes just in case. If you weighed 180 pounds on Earth, you'd only be a very light 30 pounds on the Moon. Could hop around real easily, and you'd be a bit heavier on Mercury. Not quite half as heavy, but close. A couple other things in comparison to the Earth, the mass of Mercury is little. It's 0.055 times the mass of the Earth, so it's tiny compared to our planet. Density, though, is similar, and so that doesn't affect, well, yeah, it's just similar. I mean, there's a lot of theories as to why it's similar. Maybe the formation of Mercury went through some similar processes as on Earth, but we're not going to go into that as much. So, cool. Oh, another thing to notice before I go to the next slide. You see on the Moon, these are very different. These are the Maria on the Moon. We haven't talked about the Moon yet, but that's coming up in the Earth unit. And you don't see those on Mercury. It's thought that these are lava plains on the Moon. Mercury has lava plains. You can see it's pretty smooth here, so there's probably some lava plains going on there. But they're not dark, or as dark, like you see on the Moon. So what's the difference? What's the difference? Physical properties of Mercury. Because of Mercury's low gravity, it can't keep an atmosphere. The reason why we have such a nice protective atmosphere that we can breathe in and fly around in on airplanes with wings is that Earth's gravity is strong enough to hold a little bit. Nowhere near as strong as like Jupiter or Saturn or those planets, which hold really thick, really extremely dense and massive atmospheres. Earth can only hold a little teeny sliver, just this little tiny little amount. This, by the way, this picture's from the International Space Station, and so, but it's enough for us. You can get pretty high in a plane. This is still some miles high, but on Mercury, not quite the case. I mean, there are particles in there, as we've seen from the couple of probes that we sent to Mercury, but nothing is very permanent. If anything, the particles that are in Mercury's atmosphere are only there for a few weeks or so before they escape into space. Where do these particles come from? Well, if they keep escaping, then they probably came from the sun. The sun is constantly shooting out solar wind, which contains hydrogen and helium particles, a lot of hydrogen and helium, and so Mercury's gravity will catch some of them. Not a lot, but some. Thing is, it can't really hold on to them that long, and so they disappear pretty quickly. And what makes Earth nice for life, nice and stable, is again, one thing is that it's the atmosphere, and one thing that the atmosphere does is it moderates temperature. It keeps the temperature from fluctuating wildly up and down. And since Mercury doesn't have this atmosphere, then it doesn't have this moderational influence. So the temperatures of Mercury fluctuate wildly. They go from negative 100 Kelvin to 700 Kelvin. And they can get so high because Mercury is so close to the sun. But these temperatures probably don't mean much to many of you. So let's kind of translate that into something more meaningful. The Kelvin scale is based on 0 degrees being absolute zero. Whereas in the scale we're most used to, Fahrenheit, absolute zero happens at negative 459. Whoa! So then what does that mean for 100 Kelvin? Well, if this is 273, then 100 is probably down here somewhere. Which means that's probably like negative, well, let me just bring up Google Let me pause here and bring up Google temperature converter. Okay. If you didn't know that Google could do this, I mean, it really can do pretty much anything. Just type in. Oh, I'll just leave it here. Just type in 100 Kelvin, 100 K to F for Fahrenheit, and it should bring up this nice little. Should bring up this Zigo Kelvin here. Then to Fair. What? Hold on, let me pause. Oh, I figured it out. I was in news. You want to be on the web. So you could just go 100 Kelvin to Fahrenheit, and bam. That's negative 280 degrees Fahrenheit. That's cold. And then 700, well, boiling water happens at 373 Kelvin. So you can imagine what 700 is, like way up here. Whoa! Whoa! 700. So what is that in Fahrenheit? Let's check it out. Just change this to 700. It's 800 Fahrenheit. Hot. So Mercury goes from negative 200 to 800. That's crazy. What on Earth? What's the most? If you go to Antarctica, you might get negative 60, 70. Pretty cold. To the hottest deserts, you might get what 120. That's a pretty big temperature shift, but that's not as much as Mercury. Mercury is insane. So, but one cool thing is Mercury, as I'm going to explain in a sec, Mercury's tilt, unlike the Earth, which causes the Earth's tilt causes the seasons amongst other things, Mercury's tilt is basically zero, and so the temperatures are probably pretty consistent on some places on Mercury. So if we ever wanted to build a base, we could just find the sweet spot where the temperature is pretty normal, and it might be doable. But I'm sure there's plenty of other things that would make making a base on Mercury not quite so easy. But anyway, this 600 degree fluctuation in Kelvin is the largest fluctuation of any planet or moon in our solar system that we know of. Pretty crazy. Some surface properties of Mercury. Well, Mercury has numerous craters, as we saw in the picture that looked like the moon. Mercury has plenty of craters as well. And we discussed in the Mars unit, Mars has a lot of craters, probably not as many as these. And basically every body that we see has some evidence of craters. And the theory is that, early on in the formation of the solar system, there's a lot of smaller bodies flying around. And the reason why there's not a lot now is because all these smaller bodies were kind of all sticking together. And by sticking together, I mean crashing into each other. Kind of like building a snowball or a snowman. You take little pieces of snow from here and there and bring them together to make a bigger one. And so it's thought that all the planets and moons would probably have roughly a similar amount of bombardment from meteorites happening. But depending on the type of planet, if you have lots of geologic activity and weather systems that erode these craters, then those will slowly disappear. But on Mercury, not a lot of that, and so a lot of the craters stick around. But in comparison to the moon, Mercury does have less dense crater areas. And this is probably because of lava resurfacing, more lava activity really early on in Mercury's history that would have covered up a lot of the early bombardment craters. But we don't know a lot about Mercury, and so we're not 100% sure about this. Some of the lava features commonly associated with large-scale lava flows are not present on Mercury, such as the Maria that I discussed on the moon here. These might be sort of Maria-ish, but why don't they look like this? it's an interesting puzzle for someone to figure out. Um, but anyway, we don't really know much about how Mercury's landscape formed. It's a pretty big puzzle. What else we got going on here? Well, something we don't see on the moon are these what are called scarps. They're really like ridges, or almost like cliffs. And this would be an example of one right here. And we don't see them on the moon. We see them on Mercury. So how do they get there? Well, don't really know, but we have a pretty sound theory that they probably formed after the large-scale meteorite bombardment, because they cut through a lot of these older craters. Although we think that these probably happened pretty early in Mercury's history. And they probably formed as Mercury cooled and shrank. Um, if you ever seen something shrink, you know that it wrinkles, depending on, I guess, what it's made out of. But you know, most things that shrink will tend to wrinkle because the outer layers are, if they're stuck to the inner layers as it's shrinking, the outer layers don't really have anywhere to go except in wrinkle state. And so it's thought that these ridges are really just wrinkles as Mercury cooled and shrank. Everything cools. If you haven't noticed, if you heat something up and just let it sit, if you don't keep adding energy to it, it's going to cool down. So everything in our universe seems to be cooling uh, over time, and planets aren't exempt from that. Planets take a lot longer to cool than, say, a cup of coffee, because there's a lot more material, a lot more energy to lose um, in order to cool off, and so it just takes a lot longer. But the smaller the planet is, theoretically, the quicker it would cool, because it has less material to cool off. So anyway, that's one of the theories as to why these strange-looking phenomena happen on Mercury. But why doesn't that happen on other planets or moons? Some of it may happen on some, but we don't necessarily see evidence of that. Say on the Earth, for example, if we see ridges, things on Earth, they might come from erosion or tectonic activity. But we don't really think there's much tectonic activity on Mercury, so if any, there probably is none based on what we've seen. So, um, yeah, interesting. And am I gonna? No, I'm not gonna finish this video. So, 12 minutes. Let me see here. Quick little analysis, and I'll be right back. Okay, I'm back. So, I only have a few more slides left, and I'm gonna save this slide in the next couple for the last video, the third video on Mercury, and that's all there will be. So, a pretty short unit. And so, until the third video, enjoy life.